So imagine you're just opening your banking app, right? You want to transfer, say, $30 to a friend. You hit the button, but your thumb slips.
Yeah, the classic double tap.
Exactly. You accidentally double tap send. And it seems like this tiny, harmless physical mistake.
Yeah.
But in that fraction of a microsecond, what actually happens inside the banking system?
Well, if the computer processes both of those taps at the exact same moment, you could theoretically drain your account into a negative balance
Right.
while simultaneously, like, creating phantom money out of thin air.
Which is wild.
Yeah.
And today we are looking at the invisible mathematical rules that prevent this specific disaster from happening, millions of times a second. Because as a learner in the modern world, you are interacting with massive, unfathomable amounts of data every single day.
You really are. I mean, you search, you click, you buy, and you just sort of expect it to work without the whole thing collapsing.
Totally. It's this fascinating illusion. The clean, simple interface on your screen is hiding an incredibly complex, meticulously ordered universe behind the scenes.
It is. And to truly understand how systems handle this mind-boggling scale and the chaos of it all, we're going to explore some core database architecture today. We are pulling this from an incredible set of lecture notes from the CS50 computer science course.
Right, specifically focused on their databases with SQL optimizing section.
Exactly.
So our mission on this deep dive is twofold. First, we're going to figure out how a database handles sheer jaw-dropping scale without, slowing to a crawl. We'll use the IMDb movie database as our testing ground for that.
That's a great example to use.
Yeah, and then we're going to look at that banking double tap scenario, like what happens when millions of people try to change data at the exact same time and how engineers prevent pure mathematical chaos.
So let's unpack that scale problem first, because the numbers we're looking at for the IMDb database are, frankly, staggering.
Yeah, we're talking about tracking over 400,000 movies.
It doesn't stop at movies, right? You have to track the people, too. The dataset includes more than 1.4 million stars and upwards of 200,000 user ratings.
Right.
You start doing the math on how those data points intersect, and the sheer volume becomes an architectural nightmare.
Let's ground this in reality for a second, because we aren't just talking about abstract zeros and ones. We are talking about a system that needs to instantly find Tom Hanks, Owen Wilson, or Kristen Bell among those 1.4 million actors.
Exactly.
We're talking about sorting through like Toy Story, Cars, Frozen, Wall-E.
And you have to remember, every single one of those movies has a release year. Every actor has a birth year. Every rating has a total number of votes.
Right. It's just so much data.
If you try to store all of that in a simple way, the system just breaks down.
My first instinct when trying to picture all that information is like a hoarder's garage.
Oh, totally.
Like if you just kept all this in one giant flat spreadsheet, every single row would have to say the movie name, the actor, the year, the rating. You would have to type out the letters Tom Hanks thousands of times for every single movie he's ever been in.
Right.
Stepping through that to find one specific detail would be basically impossible.
A hoarder's garage is exactly what happens when you don't have a plan. But database architects solve this by using a relational structure.
Okay, so how does that work?
Well, to upgrade your analogy, think of a highly efficient restaurant kitchen. When a waiter takes your order, they don't write a quarter-pound beef patty with lettuce, tomato, pickles, and a sesame seed bun on the ticket.
Right. That takes way too long and takes up too much space.
Exactly. They just write burger number 4. The kitchen has a separate single menu taped to the wall that explains exactly what number 4 means.
Oh, I love that. So you never repeat the ingredients, you just use a tiny reference number. How does that actually translate into the IMDb universe we're looking at?
We use schemas. They are essentially the blueprints for different tables. The architecture strips the data down into isolated, highly specific lists.
Okay.
So first you have the person table. It only stores 3 columns, an id, a name, and their birth year. So Tom Hanks isn't this massive repeating text file. He just gets an ID. He becomes ID 158.
Got it.
Owen Wilson is 5562. Kristen Bell is 68338.
And I assume you do the exact same thing for the movies, right?
Correct. You build a movie table. It holds an id, a title, and a year. Toy Story becomes ID 114709. Cars is 317219. Frozen is 229469.
So it's all just numbers pointing to things.
Exactly. And finally, you have a completely separate rating table, holding the id, the rating itself, and the number of votes. Everything is isolated.
So the data is pristine, the hoarder's garage is completely cleaned out. But wait, if everything is in separate, isolated boxes, how does the computer know that Tom Hanks was actually in Toy Story? Like,
Ah.
the tables have to talk to each other somehow, right?
That is the magic of a relational database. They communicate through what we call junction tables. This is a brilliant structural shortcut.
Okay, how so?
You create a tiny, lightweight table, simply called stars. And the only job of the stars table is to hold two numbers next to each other, a person ID and a movie ID.
Oh, wow. So instead of a massive bloated row that says, Tom Hanks, born in 1956, starred in the 1995 movie Toy Story, the stars table just has a tiny row that says 158 goes with the 15709.
You've got it. It is incredibly elegant. And there's another junction table called HAS that simply connects a movie's ID to its rating ID.
That saves so much space.
Massive amounts of hard drive space. But more importantly, it prevents human error. If someone misspells Tom Hanks in a flat spreadsheet, a search engine might never find that movie. But an ID number of 158 is universally consistent.
Okay, I'm completely with you on the organization. We've built the restaurant kitchen. The data is structured beautifully.
Yep.
But let's look at the actual mechanism of searching, because I see a massive speed bump here. Even with perfectly neat tables and ID numbers, if you want to find the movie Turning Red or Wall-E among 400,000 rows,
Right.
like if you just start at row 1 and read down the list, that is going to be painfully slow.
It's what software engineers call a linear search. At scale, a linear search is the absolute enemy of performance. If Turning Red happens to be the very last row in your database, the computer physically has to check 399,999 rows before it finds it.
And nobody sitting on their couch with a remote control is going to wait for that to load. So how do systems bypass the linear search?
This brings us to the concept of indexes. To fix the speed problem, engineers use a specific SQL command called createIndex. And to verify that it's working, they use a diagnostic tool called explain query plan.
Let me throw out another analogy here to see if I'm grasping the mechanism.
Before it.
If I'm holding a 1,000-page biology textbook and I need to find the definition of a specific cell membrane, I do not start reading from page 1. That's the linear search.
Exactly.
Instead, I flip to the index at the back of the book, which is perfectly sorted alphabetically. I find the word, I look at the page number, and I jump straight to page 842. I basically skip over 99% of the book.
That is precisely how a database index operates.
Right.
It is a secondary data structure created for one purpose.
Okay.
Speed.
Okay.
When you run explain query plan on a search, it acts like an X-ray. It tells you how the computer is finding your data. Is it doing a slow, linear scan of every row? Or is it cleverly jumping straight to the answer using an index?
That makes sense.
And the most important mechanism behind these indexes is a structure known as the B-tree.
I really want to spend some time on this, because I hear the term B-tree thrown around a lot in computer science, but I want to understand the actual math of it. It's described as a balanced tree. What does that structural shape actually do to the computer's speed?
It completely changes the mathematical reality of searching. Think of an upside-down tree branching downwards. At the very top, the root node, the computer asks a single question to split your entire data set.
Like, what kind of question?
Let's say it asks, is the movie ID higher or lower than 500,000? Now, if you're looking for Wall-E, which is ID 911970, the computer goes down the higher branch.
And by making that one single decision, it just ignored half the database. 200,000 movies are instantly eliminated.
Exactly. Now, follow that branch down to the next node. It asks again, is it higher or lower than 750,000?
50 goes higher.
Another 100,000 movies eliminated. This is the mechanism of halving.
Let me just play this out. You start with 400,000. One question gets you to 200,000. The next gets you to 100,000. Then 50,000.
Keep going.
Then 25,000. 12,000, 6,000, 3,000, 1,500, 750.
You see where this goes. By the time you ask about 18 or 19 yes or no questions, you have pinpointed one single movie out of nearly 500,000.
Under 20 steps to search 400,000 items, that is a mind-blowing realization.
It really is the absolute core of why the modern internet feels instantaneous. And the reason it's called a balanced tree is critical.
Why is that?
If the tree wasn't balanced, meaning if one branch held 300,000 movies and another branch held just 2, the search times would be unpredictable and chaotic. Balancing ensures that every piece of data, no matter where it is, can be reached in a roughly the same tiny number of steps.
Okay, that makes the how completely clear. Now, I know there are a couple of specialized indexes used for different scenarios in the notes. What exactly is a covering index?
Let's stick with your biology textbook analogy. Imagine you flip to the index at the back of the book to look up that cell membrane. But instead of just giving you page 842, the index itself actually prints the full two-sentence definition of the cell membrane right there next to the word.
Oh, so I don't even need to open the main part of the book at all.
Exactly. A covering index is an index so comprehensive that the data you are querying can be retrieved directly from the index. The computer never have to expend the energy to jump back and check the main table. It is the ultimate architectural shortcut.
And what about a partial index?
A partial index is a way to save space. It's created using a where condition to only include a specific subset of your rows.
Can you give an example?
Sure. Let's say you run a streaming service, and you know your users search for new releases 90% of the time. You wouldn't index all 400,000 movies. You create a partial index where the release year is greater than 2020.
Oh, nice.
The index stays small, lightweight, and incredibly fast for the things people actually want.
That makes perfect sense. Before we move on from reading data, there is one database maintenance command from the source that caught my eye. Vacuum.
Ah, yes. Vacuum.
Why does a database need to be vacuumed? Does data leave behind dust?
It leaves behind digital potholes. When you update or delete a row, say you remove a canceled movie from the database, the hard drive doesn't magically shrink to close the gap. It just leaves an empty block of space sitting there.
Oh, I see.
Over time, as you delete thousands of things, your database becomes fragmented with these empty potholes. It slows down the reading process. The vacuum command is the mechanism that essentially paves the road. It reorganizes the database, reclaims all that unused space, and packs the data tightly together again so everything runs efficiently.
Okay, so we have schemas organizing our data like a restaurant kitchen, and we have B trees acting as these hyperfast textbook indexes to retrieve that data in less than 20 steps.
Right.
That is brilliant for reading information. But what happens when we switch gears to writing data? Because this brings us to the second part of our mission, concurrency.
Concurrency is where database engineering transforms from a structural puzzle into an incredibly stressful high-wire act.
Yeah.
We aren't just dealing with one person reading a movie title. We're dealing with thousands, sometimes millions, of users interacting with the data simultaneously.
And this brings us right back to our banking hook from the start of the deep dive. Let's look at a simple accounts table. 3 users. Alice has a balance of $10, Bob has $20, and Charlie has $30.
A peaceful, orderly financial ecosystem.
Right, until the double tap. So here is the scenario. Charlie is trying to transfer his $30 to Alice, but his thumb slips. He accidentally initiates a second $30 transfer to Alice at the exact same time.
The nightmare begins.
And just to make it a total nightmare, Alice is simultaneously at an ATM trying to withdraw $60. Now, I have to stop here and challenge the premise.
Okay.
Computers operate at light speed, but they still do things logically. Wouldn't the central processor just take the very first click, see that Charlie sent his $30 to Alice, update his balance to 0, and then politely reject the second click because the money is gone?
In a purely sequential world, yes. That is exactly how a human teller would handle it. But because of concurrency, these actions are not waiting patiently in a single file line. They are firing in parallel threads. They're running side by side.
Okay.
This creates a terrifying mechanism known as a race condition.
Walk me through the exact microsecond this fails.
Let's call Charlie's 2 accidental taps transaction A and transaction B. They launched parallel to each other.
Yeah.
Step 1. They both need to check Charlie's balance to ensure he has enough funds.
Right.
Transaction A looks at the database and sees $30. At the exact same microsecond, transaction B looks at the database and also sees $30.
Oh no! They both think he has the money.
It gets worse. Because they are racing without communicating, they both perform the math independently. Transaction A says, great, subtract $30 from Charlie, add $30 to Alice. Transaction B says the exact same thing. Subtract $30 from Charlie, add $30 to Alice.
But there is only one pool of $30.
Precisely. The math starts shifting under their feet. Transaction A might push Alice's balance to $40. A microsecond later, transaction B tries to push it to $70 while forcing Charlie's account into negative $30.
That's insane.
The database suddenly realizes the internal logic is shattering. The rules of math are being violated. This clash results in a system error known as a chi-check constraint failed.
So what happens? Does the bank just lose the money into the digital void?
Well, if left unchecked, yes. A race condition could literally invent money out of thin air or destroy it entirely. Ellis could walk away with cash that never existed, while Charlie gets penalized for a negative balance. It is the ultimate systemic failure.
That is legitimately terrifying. So how do the architects who build the global banking system prevent a clumsy thumb from collapsing the economy?
They tame the chaos by wrapping these vulnerable operations in what we call a transaction. You could think of a transaction as an invisible protective bubble.
Okay.
It's the single indivisible unit of work. When Charlie hits send, the database issues the command begin transacting.
The bubble goes up.
The bubble goes up. Inside that bubble, the computer does the reading, the math, the subtracting, and the adding. If every single step works perfectly, it reaches the end and issues a commit command.
And then what?
The bubble pops, and the changes are permanently carved into the hard drive.
But what about the second tap? What if it hits that cheat constraint failed error halfway through the math?
If anything inside the bubble goes wrong, the database triggers an emergency stop called a rollback. The rollback acts like a giant undo button. It completely wipes away the messy, half-finished math and returns the entire database to the exact pristine state it was in before the transaction began.
Okay, the bubble makes sense, but what are the actual rules governing that bubble? How does the database judge what is safe to commit and what needs to be rolled back?
Database engineers enforce safety through a set of 4 unyielding laws. You could think of it as the database constitution. It was forged from the ashes of historical data catastrophes.
The database constitution, let me see if I can guess the architecture of these laws. The first rule would have to be that you can't do half a job. Like you can't take the money from Charlie and then crash before giving it to Alice.
Spot on. That is the first law.
Yeah.
Atomicity. A transaction is all or nothing. It cannot be fragmented. It either entirely succeeds or it entirely fails.
Okay, but what if the whole package succeeds, but it tries to do something illegal? Like, what if Charlie's transaction successfully pushes his balance to -50, and the bank has a strict rule against negative balances?
That brings us to the second law, consistency. The transaction must leave the database following all of its predefined rules.
Right.
If a commit would violate a core rule like an account dropping below 0, consistency demands that the transaction is rejected and rolled back. It ensures the data remains logical.
All right, but even with atomicity and consistency, we still haven't solved the double tap.
Bro.
If transaction A and transaction B run at the exact same time, they're both all or nothing, and they both think they are following the rules based on the $30 they saw.
And that is why the third law is the most crucial for concurrency. Isolation. Isolation dictates that no matter how many parallel threads are running, the database must process them as if they are completely alone in the universe.
Wow.
They cannot see each other's half-finished work. They cannot interfere.
I'll hold my questions on how that physically works for a second. What is the final law?
Durability. Once a transaction gets the green light and commits, it is permanent. If someone trips over the power cord to the server a millisecond after the commit, that money is still safely in Alice's account when the power comes back on.
Good to know.
Together, these 4 laws, atomicity, consistency, isolation, and durability, form the acronym ACID.
ACID. The database constitution. I love that. But I need to go back to isolation because this is where the theory has to meet the physical hardware.
Okay, let's do it.
I understand the rule of isolation, but if I am listening to this and wondering, like, what does the computer actually do to isolate Charlie's first tap from his second tap? How does it physically stop transaction B from looking at the balance?
The mechanism it uses is a system of locks. And to answer your unasked question, a lock isn't a separate file or a complex program. It is physically just a tiny flag, a single bit of memory, acting like a do not disturb sign hung on a specific piece of data.
Oh, okay.
There are 3 states of these locks. The default is simply unlocked. The data is sitting idle.
Anyone can walk up to the door.
Right. The next state is a shared lock. A shared lock is issued when people just want to read the data.
Right.
If Alice and Bob both log into their apps at the same time just to look at their balances, the database hands them both shared locks.
Makes sense.
Reading data doesn't change anything, so the system safely allows millions of people to read the menu at the same time.
But writing data is the dangerous part.
Which triggers the final state,
Yeah.
the exclusive lock.
Yeah.
The absolute microsecond Charlie's first transaction starts its transfer, the database slaps an exclusive lock onto Charlie's account row.
So what happens when the second transaction hits that door?
It acts as a concrete wall. Nobody else, not even Charlie's own accidental parallel thread, can read or write to that row. Transaction B crashes into the exclusive lock and is physically forced to wait in line. It cannot even look at the $30. It is held in stasis until transaction A finishes its math, commits the successful transfer, and removes the lock.
Oh, and by the time transaction B is finally allowed through the door, the reality has changed.
Exactly.
Transaction A has already dropped Charlie's balance to 0, so transaction B looks, sees $0, realizes it can't proceed, and safely rolls back. The race condition is completely neutralized.
You got it. The lock forces the terrifying chaos of parallel threads into an orderly sequential line. No phantom money, no system collapse.
That is just an incredibly elegant piece of engineering. So let's step back and look at the whole journey we've taken through this invisible infrastructure.
It's been quite a ride.
We started with the sheer terror of massive scale, the hoarder's garage of IMDb data. We learned how organizing that data into relational restaurant menus with ID numbers keeps the information pristine. Then, we explored the incredible math of B trees, cutting 500,000 records down to just 20 steps so we can retrieve data instantly. And finally, we dove into the chaos of the race condition, discovering how the rigid constitutional laws of acidity, backed up by the concrete walls of exclusive locks, save our bank accounts from collapsing under the weight of human error.
It truly is a remarkable system. We take it for granted, but without those schemas, the halving math of the indexes and the strict enforcement of locks, the entire information age simply wouldn't function.
And that brings me to a final thought I want to leave you with. Something you can actually spot in the wild now that you know how the plumbing works.
Oh, I like where this is going.
Next time you are buying concert tickets online, or you are booking a flight, and you finally get through to that checkout screen, you know the one I'm talking about. It has that stressful, glowing red timer ticking down telling you, holding your seats for 5 outer minutes.
Oh, the dreaded timer. Everyone knows that panic.
Exactly, the panic. But realize this, you are not just looking at a high-pressure marketing tactic to make you pull out your credit card faster. You are actually watching a database's exclusive lock happening in real time right in front of your eyes.
That is exactly what it is.
It is a real-world manifestation of the exact transaction principles we just explored. The system has drawn a protective transaction bubble around those 2 specific aisle seats. It has hung a do not disturb sign on them, ensuring that nobody else on the planet can swoop in and trigger a race condition while you type in your security code. It is literally holding the chaos of the internet back, just for you.
That is a brilliant way to look at it. A perfect everyday example of isolation doing its job.
So the next time you see that timer ticking down, you don't need to panic. Take a deep breath, appreciate the bee trees that found the tickets, and thank the architects for the lock. You are protected. Thanks for taking this deep dive with us. We'll see you next time.